Right, so next I just wanted to make a few comments about the model order. P, in other words, the number of poles that we actually have in the all-pole model. So choosing an appropriate P is usually based on this average total prediction area, or just average prediction error. And let's just write that down in the two cases, the two methods, right? The autocorrelation method, we had the following for the total prediction error. So this one is the sum n equals minus infinity to infinity. And we've got in here S of n, then minus this sum k equals 1 to p. And then a, k, we'll put a coefficient of p there as well, or a superscript of p. And then S of n minus k. This quantity squared. And then also just to note here, E of 0 then would just be the sum of the S of n squared. So then we can look at a function which he calls script v of p. We define that script v of p to just be the total prediction error, or average prediction error at p, and then divided by this case of 0. Okay, and of course we have control over this being non-zero from the previous discussion that we had as well. So this thing can be plotted just as a function of a real valued function of p. And what happens then is that typically the designer of the system or of this model can look for a flattening of this v sub p for some, let's call it, let's just call it p0. In other words, at some point, this function is actually going to start to flatten out, and then we can choose a value which is after that point. So for p greater than p0, not much is gained, essentially. So basically, this at this point, the procedure is kind of ad hoc, but you just take a look at this function and try to pick a value that seems reasonable, not on any particular formula, but just the fact that this function is flattening out. Okay, so then let's take a little bit of time to look at all-pole spectrum analysis. So basically, this all-pole signal modeling that we're doing this can be used to get estimates of the signals spectrum from truncated or windowed data. So after all, what we're doing here is picking up different types of signals, and we're modeling them with an all-pole filter, which means we choose an input to the filter and we try to get the output close to our signal S that we're modeling, right? And of course, since we're modeling signals, then we're also getting models of their spectrum, right? So how could this be used? In the deterministic case, where we had the deterministic case, remember we had input V is just given by an impulse, right? We get the following. If we take S hat of e to the I omega, this is now Fourier transform. So frequency content, this is given by h of e to the I omega squared, and then the input signal V, also spectrum of that, e to the I omega squared, which of course for the delta impulse, right, this is just going to be 1, and so this whole thing is just h of e to the I omega quantity squared. So that's in the deterministic case. And then for random signals, the other case, now the input, remember, is going to be white noise. Well, we can't just for random signals, we can't just simply take the spectrum, right? Because when you talk about random signals, you talk about properties of the signals as opposed to the specific signal itself. So what kind of properties can we look at? Well, again, we can look at the autocorrelation function, and then in fact we can form the power spectrum. All right, so that looks like this. So we get P S hat of e to the I omega. There are a lot of different notations for the power spectrum, but again, what we're going to get here is h of e to the I omega squared. Again, this is our all-pole filter. That's where the system function h is coming from, right? And then we get, then here we get P WW. So this is the power spectrum of the white noise input, and then this is just going to be now again h of e to the I omega magnitude squared. Okay, and that's again because this is equal to 1 for white noise. Should probably say a little bit more about power spectrum. So P equals power spectrum, and this is just actually equal to the dt discrete time Fourier transform of the autocorrelation. So how does that look actually? So power spectrum of omega. Here we've got it subscripted with the S hat signal. But if you think of it just as a function of omega, which is more like we would be writing it in Math 320 and 321, then this would just be the sum n equals minus infinity to infinity. Here we've got a signal going in here. Let's just call this is S. Okay, and then we have at some value n, and then e to the minus I 2 pi omega n. So we've got the discrete time Fourier transform of the autocorrelation function. And I'll start with that next time and talk about some properties of the power spectrum also.